All right, today we are diving into something that feels like it's straight out of science fiction. We're talking about a class of materials that seem to just completely break the rules of physics, behaving in ways that are so counterintuitive you'd swear it was magic. But as you're about to see, it's not magic at all. It's just brilliant, brilliant design. Okay, so let's start with something super simple, something we all know. Just picture a rubber band. You grab both ends, you pull. What happens to it right in the middle?
Yeah, exactly. It gets thinner. That's true for pretty much every single material you see every day. You stretch something, it gets skinnier in the middle. It's one of those basic facts of life we just don't even think about.
Now hang on a second. What if you pulled on that rubber band and instead of getting thinner, it actually got wider? What if you squeezed it and it got narrower? Sounds totally impossible, right? Well, it's not.
So let's jump right into this bizarre world. We're talking about materials that seem to have read the physics textbook completely upside down.
They're called auxetic materials, and this incredible property, getting fatter when pulled and thinner when pushed, is way more than just a cool party trick. It actually gives these materials some amazing advantages, from absorbing insane impacts to resisting fractures.
This chart just lays out the difference perfectly. On the left, that's our everyday world. You stretch it, it thins out. On the right, you have the total opposite. This isn't just a small change, it's a complete reversal of how we expect stuff to work.
So, how in the world is this even possible? Is it some exotic new element? Some kind of unobtainium? Nope. The secret is actually much, much cleverer than that.
So here's the crucial idea. We're talking about metamaterials. See, you can make an auxetic structure out of almost anything. Steel, rubber, plastic. The magic property doesn't come from the stuff itself, but from its tiny, meticulously engineered internal architecture. It's all in the geometry.
And that geometry, well, it can take on some truly beautiful and fascinating forms. So let's take a quick tour through a gallery of some of the most common auxetic designs.
And you can just see the sheer variety we're dealing with right here. These aren't just random patterns, Each one of these little repeating shapes, these unit cells, is like a tiny engine, designed specifically to create this impossible behavior. Let's look at a few up close. This is one of the absolute classics, the reentrant honeycomb. You see how the sidewalls kind of point inwards? Well, when you pull the whole thing vertically, those hinges are forced to open up, which in turn pushes the entire structure outwards. This mechanism makes it incredible for soaking up energy, which is why it's a go-to for things like impact protection. Or take the star-shaped geometry. This is another really popular one. Here, when you pull or push on it, the arms of the star flex and rotate. This distributed motion makes it super compliant and just great for things like protective padding that really needs to conform to whatever surface it's on. But maybe the most mind-bending example of all is origami. Seriously, you can take a simple, flat sheet, fold it in a very specific pattern, and suddenly you have a complex 3D structure that has these bizarre auxetic properties. It just goes to show how powerful pure geometry can be.
So all this is fascinating in theory, but where are we actually seeing these impossible materials making an impact in the real world? Okay, let's look at the applications.
This is where it gets really amazing. On the screen, you're looking at the whole process. A patient's CT scan is used to design a perfectly fitting spinal implant. That design, with its special auxetic lattice inside, is then 3D printed. This isn't sci-fi, this is custom-designed material science happening today.
And it definitely doesn't stop there. The applications are just exploding. We're talking bike helmets that get denser at the point of impact, medical stents that can expand perfectly inside an artery, even huge deployable structures for satellites that can unfold in space. The list just goes on and on.
So what's the big takeaway from all of this? What does the rise of these auxetic materials really mean for our future?
Well, it comes down to this really powerful idea. We're moving away from a world where we have to find the right material for a job, and we're entering a world where we can design the right material for the job. You need extreme shock absorption? There's a geometry for that. You need something that can change its shape on command? There's a geometry for that too. And that leaves us with just a fascinating question to think about. We figured out how to program behavior directly into the structure of matter itself. The possibilities aren't just being discovered anymore, they're being invented. What once seemed impossible is now just another design challenge waiting to be solved.